Recording has started.
Yeah, so we will talk about the optimization. So this time, basically, this is not like a class optimization. So we will not talk about the convergence analysis or any more complicated math here. So we will more go through the main methods, which is used for deep learning. That's why I mean say the stochastic optimization for deep learning, so that you know you could use that to train models. Yeah, so this is more just describing algorithms and then what happens some hyperparameters, how to interpret those hyperparameters. So that's about it. Okay, so that's yeah, that's the data. So it's relatively big. Okay. And if you already have some experience, you probably already heard many of these algorithms. So this essentially just reinforce some concepts you get. And also probably just helping to you to understand some of the hyperparameters a little bit better. Let's move on. So yeah, so these are topics, right? The topics basically has SGD, right? So that is a basic workhorse for all the current machine learning. Essentially, at least for the deep learning, so they're all gradient based. They are stochastic gradient descent. So we will quickly talk about that first. Then we talk a little bit about the learning rate. This is also actually important topic. Both theoretically, a lot of people study that, including some of our work looking at this issue, and practically it matters. How do you set learning rate? And yeah, we just talk probably a simple one, the learning rate schedule. There are actually more complex ones. Maybe we can put that into the reference later. That momentum is important. So there's one. There are a few important things, right? Two important things in the SGD. One is momentum, which is a classical concept. So it appeared, I think, in the 80s or even earlier. So and it's pretty effective. And we will talk about that, not the theory, but just what you expect, and the parameter. The other important concept is adaptive gradients. This is we mentioned a bit about gradient vanishing, right? So we mentioned the rest, the residual, the ReLU is a part of method that can be as a treatment of that. But here, the adaptive method is another one, right? So this is from the optimization perspective, is somewhat I believe it that problem, and that's why it's effective, important. This one comes up in much earlier, much later. I think it's a 2010 paper. The paper is already given there. Then it evolves. Later on, I think the key algorithm, a lot of algorithm, especially nowadays, people focus on transformers. For the earlier networks, people try to use SGD and so on. But for the transformers, somehow it's hard to train with SGD. So they are almost all atom based, right? So that's the latest. They're still evolving. There are some new optimizers coming up, right? They are discussing like muon and so on, but we will not talk about those. Those are much more recent. Also not established, but Atom W definitely pretty much established. So this just covers the topic. We'll quickly talk about what these methods are and some parameters which involved with this method. How you should be interpreting those parameters. Okay. Okay. So just recall, right? So this is essentially a recall. about our notation. So this is training data. And this is training objective. Training objective, recall that we have this F is a neural net, which we have talked about last time. F data, right? Data is your trainable parameters of your model. So that the idea is you can take gradient of the model, right? L is a loss function. The loss we talked about cross entropy loss. We talked about least squares loss, right? The last time. So basically, and once you put that together, you get the objective function. Then there's a regularizer. Regularizer is lambda R, right? So this one appears in quite many of the methods. As a so-called weight decay. So we will talk about that. So usually we look at L2, so in the neural net literature. And again, the regularizer is used to stabilize the iterates. And we will see explicitly because it's a shrink the weight, right, called weight decay. That actually has the explicit effects of that. So anyway, so this is what we have seen last time. Now I just want to do a little bit of simplified notation because, if I write something like this, it's just pretty many symbols, right? I just say, oh, this is a function of theta with index I. So this one is later on, that's what we would use. Here is the example. So the example we can go quickly. Basically, this is a ridge regression, classical machine learning, right? So logistic regression for neural nets. This one we have showed that last lecture. So this is basically your pass through softmax. This loss is a negative log likelihood loss, negative log of your likelihood. Softmax is a likelihood, right? But if you think about the logits, usually F is a logits. It's called a cross entropy. Basically, yeah. Basically, this is this is essentially what it looks like for the example. As I mentioned, the notation, if you have an F, you have an XI, YI, right? So it's a little bit, notation-wise, it's complicated. You don't have to, when you talk about optimization, stochastic optimization, you just know, given loss function passing through one data point I, you can compute the gradient, right? Just using the backward. Once you write forward function in your PyTorch, the backward compute gradient, which is respect to your theta. So only thing you know is that. So basically, this is just the whole objective on the training data I of your theta. So we just simplify this notation, and basically this is one training point each one, and then you have this simplified notation. Okay, so yeah. So basically, once we have this and this one. Right. So then, yeah, this one basically just say I simplify this notation. You can write like whatever the loss, just using this. So this one just saying we do throughout the following slides, we will do a simplification of this notation. So that's all. It's just an example. Okay, so let's move on. Now, we first talk about, let's talk about the first most classical optimization literature, right? That's a traditional way to doing things, not using stochastic gradient descent, but gradient descent. And there are convergence theory, there are a lot of things about that. The gradient descent algorithm is the following. So you first pick a learning rate, and the initial, usually for the neural networks, initial theta 0 is a random. Right? It's a random initialization, which is properly initialized. And then what you do is you do this gradient. Basically, this one taking gradient, you first taking gradient with a loss. This guy is here, right? Second, you're taking gradient with a regularizer. and this is a regularizer. So basically, this is essentially the whole updating formula for gradient. Gradient descent. Yeah, it's a basically it's a also called a steep descent and so on. Essentially, you're looking at the fastest local function of your objective, try moving down. So this direction, you're moving down. The objective guaranteed to be decreasing if eta is small enough. So eta is called learning rate. There's one problem. So we quickly mention here is that for the full gradient descent, which would be the classical optimization, you need to do a sum over all the data, right? There are several issues with that. So for all the data, first it's very slow, right? So you go through data once, you have to just do one update. So that's one thing. The second thing, which is also important, is practically it can be tricky to do, right? You go through data are, I think it's related to the same, but essentially nowadays, if data is very, very large, right, you have to get the data from all different machines, all different GPUs to calculate this. So this can be, you cannot store that in memory. So you have to, each time you actually need to do more efficient in memory. So this is an issue of that. And the stochastic gradient method naturally say instead of summing all the data, I'll picking either one or small batch. But we will first talk about the classical stochastic gradient and not mini batch version. Then we'll come back to the mini batch, right? So yeah, if you think about that, basically. There is the main part is just computation. You're treating off basically your computation. You have to be on the whole data set. And if you have a small data set, it's okay. If you have 100 or whatever, but if you have a large data set, it's a problem. So this is where we want to do stochastic gradient. Again, we have this objective function which we have shown before. Basically, a working example of this kind of objective is this cross entropy with neural net, right? So you can think about that. So stochastic gradient descent, let's do the original version. Pick eta. I mean, again, you pick it. Let's look at the single constant learning rate and the initial data. And you do this, right? This one, in the theory, usually what you are talking about is I is choosing uniform at random problem. That's typically stochastic gradient theory is. In practice, it's slightly different. Doing permutation, I will comment soon. And then each time you just look at one data. Right. Then use it. So instead of using all the gradients, we're using one. And what is the trade-off of that? The trade-off is you actually trade off the whole accuracy using the so-called unbiased estimate of your gradient because you are looking at one direction, one data, but you introduce variance. Basically, you trade off the speed versus noise. You just have one single computation. You're doing updates much faster, but it's a noisy updates. So that's typical trade-off. Practical implementation is the following. If you look at it, usually they are not uniformly picking random from 1 to n. Essentially, they randomly permute the full training data, right? And once you permute, actually you need to reshuffle every epoch. That's also important. You need to keep on. You do not want just using fixed random permutation going through all the epochs. That one causes some problem, causes you slow convergence for many problems. You can try if you want. But each time you randomly permute, right? And then you go through this random permuted data, not every time. So this is more practical. And this is, if you look at how the data loader is implemented in the modern learning like PyTorch, that's basically what happens. And each of these random permutation, and then you go through this random permutation once over the training data is called epoch. This generally actually converges faster. That's why people don't do that instead of doing this. And theory-wise, it's less developed than this. A lot of theory working on that. There are some small theory trying to explain why this one could be better than this. But anyway, so this is from a single SGD implementation. Now we move more serious. This one actually is not what implement in reality. The reason is we will come to the next, right? It's called mini batch, right? The reason is for GPU computation. When you look at the GPUs, right? GPUs they are trying to do parallelize the computation. Usually you have to use the full GPU computation. If you just have one data going there, they just treating one data. It may not exhaust the GPU capacity. Therefore, you want to say each time instead of using one data, I have maybe 16 data, 32 data, whatever, many more data. When you do many more data, then until your GPU memory allows, and that is where the maximum you can do in parallel. So you increase the so-called batch size. Instead of looking at one data at one point, you actually look at the set of so-called mini batch at one point. Right. Again, the way I'm written here is just a random selecting from your training data of a batch size of say B. Right. In reality, it's a random permutation. You truncate that up to a batch size of B chunks and until your data. There's an issue about last data, right? So if the number of data n is not cannot be divided by B, what happens, right? So in the last one, then you have a different treatment. You can say you ignore that, or you're just using that at a different batch size. So there are options usually allow that. But essentially, the real implementation is you put that into the whole permutation once of your training data, then you partition into chunks of B, and then you go through that. So that's the implementation. Okay. But for simplicity, I will just write here. This is a more theoretical type of description. And yeah, so basically mini batch. And the reason mini batch, usually you want to go a larger mini batch as possible, allowable by GPU. Once you have a too large, it will exhaust your memory. It will have basically out of memory issue. So then you cannot increase that further. But before that, it's a good to increase. The reason is it doesn't cost you additional computation because of parallelizability. So this is the single most useful reason why you use that. You want to do a parallelizable computation at each iteration. I mean, if your GPU memory is small, sometimes you can fit only one batch if you're large data or large model, or even you couldn't fit even one batch. In that case, you have to do additional parallelization, and which we will not talk about here, but it's also topic. How do you want to deal with that? But anyway, so this is B is to help you to improve your GPU. Okay. Now one question is, right, so when you increase batch size, what happens? And think a little bit about that. Increase batch size, what will happen? Right. This one will come back. I think in the little bit later, but soon we'll come back to that. But you keep that in mind. What is the effect of batch size? Because this is a hyperparameter when we talk about the optimization of it. And it's one of the kind of important, but not the most important. More important is the learning rate. Right? Learning rate is always more important than batch size, but batch size is also important. We will talk about what happens when learning rate changes or batch size changes. Now you can think about the right. How does the mini batch gradient descent compare with the gradient descent and the stochastic? Right. So it's in between. Right. When your mini batch size n is it's a gradient descent, you update very slow. You update, but then you can fully parallelize. Actually, gradient descent is parallelized one thing. And then you update quicker. but here it's in between, but you take advantage of your GPU parallelization. Now let's look at this, right? So we talk about the regularization, but the only thing we care about, at least here in this class, for the practical purpose of, or common purpose of neural net training, is this L2 regularizer. So basically, R is 1/2. This one we have shown that before in the last lecture, and so on. So what do you actually do? So if you do the calculation, right? Basically, let's look at the mini batch gradient design. Right? So this one is data minus eta. Remember, this is a gradient of your regularizer. And when you do this calculation, you realize that this one actually is this one is your gradient of your law, right? So regularization becomes shrinkage of your model parameter. This is why it's referred to the weight decay in the in the neural net literature. So they always say, even whatever, right? There is a hyperparameter in your optimizer. It's a rate decay. What it is basically L2 regularization with a certain strength, lambda. And then this lambda will get to the decaying rate. And actually, it's a when you change the learning rate, right? The larger learning rate, the faster decay, but because they are compensated. So essentially, what you specify is not lambda times eta times lambda. It's more is lambda matters, and lambda is separate from the learning rate. So you do not want to say this is a rate, right? Basically, rate is lambda. So that's essentially how it works. But essentially, referred to as a weight decay. And this is what we need to know about the regularization. So just changing the formula a bit by shrinking. Intuitively, you can think about that. Why it helps, right? If you shrink the weight, yeah. Question?
Isn't regularization implemented so that the weights remain small? Why then do we need weight decay? Or are they just like two words for the same thing?
The weight is small. It's because when you do the update, you always shrink the weight. Weight becomes small. It's just mathematically equivalent.
What do you mean?
Mathematical equivalent. This is objective function.
Okay.
This is optimization procedure. When you have an objective, it's eventually when you actually to train the model, you are minimizing objective using optimization, right? From here it gets here. Yeah, this is equivalent. You say what you want to in your optimizer, and that becomes weight decay. And then what effectively, because each time you shrink your weights, it makes the weight small.
Good.
Yeah. Okay. Yeah, but basically this is intuition. So we are only at this intuition level. So for this, and essentially it shrinks the weights, right? So okay, so let's try to move on. Now we look at the batch size effect. So we are thinking about looking at what happens when you change the batch size, what happens to the learning rate. Again, learning rate is a little bit more important, but the batch size matters, right? If you draw, I mean, intuitively you can think about what is when you use more data, right? Using more data, of course, you have less noise, right? So that's the intuition. You have more data to average, less noise. That's what it shows. Here, this is a batch size 1, which is basically the most noisy. This is a training epoch, right? Remember epoch, each epoch is one go through the data using the permutation, and you truncate your batch size one by one, right? So that's called a epoch. This is a training loss. We only care about training loss. Now at this point, we will see the test loss in the soon, but then here is that. And then batch size 4, you have the last one, right? Batch size 16, right? You have this guy. Right? So basically, the larger, the smoother the going the training loss is. So that's what you expected, right? So and certainly increased training batch size will smooth your conversion. So that's a positive effect. In addition to the learning batch size 1. And this one, again, this is all assuming you have a constant learning. You are not changing the learning, just looking at these. And this is a test loss, right? Test loss similar, when you have batch size 16, you're going smooth. Okay. So basically, yeah, basically this is how it looks like. And you can also look at the accuracy, which accurate because loss usually is like a process entropy, whatever. It's a continuous. So accuracy is a discrete, right? 0, 1, and so on. Usually it's more noisy because it's continuous. But and also they are all pretty close to 1, so therefore there are some variations. But roughly, you will have similar, right? At least in the green, which correspond to the larger batch size, it's a smoother. So basically, yeah, I think the interpretation of this one, which is just want to illustrate, is that you actually increasing batch learning rate, increasing batch size with a fixed learning rate, it will make your updates smoother. Basically, it's a loss, it's a more smoother decrease, and so on. So this is this is basically the updates about. Okay, let's look at the other. Turns out the learning rate is more important. If you say single most important variable, probably I would say learning rate, right? So batch size is also important, but let's say fixed batch size now, looking at the different learning rates, right? The learning rates, the question is, okay, so what do you think about learning rates, right? So this is something you can, when you increase the learning rate, what happens, right? So when you decrease the learning rate, what happens, right? Here is basically shows that with the same batch size, and let's say this one is a learning, very small learning, right? It's a very smooth decay, even with the batch size 4. But it's slower. The decay speed, if you look at it, slower. So because each step is small, taking very small steps. But then because small steps makes noise less. Actually, if you do the analysis, right, usually the noise effect is learning rate squared, so that when you decrease the learning rate, the noise, the mini batch noise, decreases even further. That's why when you average out, it's actually smoother. So basically, noise reduce. You can think about the noise is reducing. Okay, learning rate decays by a factor of 2. Noise variance decays by a factor of 4. Basically. So and then essentially you get this. Oh, sorry. So basically, yeah. I think that's right. So here is a little bit larger. Actually, which one? Oh, a little bit larger is I think it's this one. Yeah, this one. It's still smooth. This one is still smooth, but I mean, gradually when you increase the learning rate, you see that it actually converges faster. So for practical reason, if stability is not an issue, noisy is not an issue. Just look at the too large learning rate starting to be very noisy, right? If stability is not an issue, you want to go as fast a learning rate as possible. Right? So this is why it's a single most important. It will affect your convergence speed. You want to try to make sure your learning rate is as large as you have for in some way. If you even further larger, what happens? I think I didn't show here. You can show that even in the deterministic case, not stochastic case, it can blow up. With too large learning rate, it can actually blow. The loss will goes to infinity. If not convergent, goes up. So that will happen, both mathematically and practically. So that happens. But if you are stable, if you're not too noisy, just looking at this learning rate, right? This guy is 0.1 is the best. Just looking at this. Okay, so that's basically, you want to go as fast, larger learning rate subject to is not causing trouble. So this is just a rule of thumb. Then here is the same. Basically, it's test. I think we just go quickly. It's basically the same, right? This guy is slow learning rate, but it's smooth, right? Once you go upper learning rate, it go faster, but then it's become noisy in the end. So that's essentially okay. The takeaway from the learning. You want, but in practice, you want to do as large learning rate as possible, just to accelerate your computation. Now, let's look at this. So learning rate, since it's very important, there is additional topic instead of batch size. Usually you just set it to be a number which your GPU can afford, right? So that's relatively simple for the batch size. Or your parallel, you can use multiple GPUs. So basically multiple GPUs, number of GPUs determine, and your model size determine how much batch size you can do. So that's essentially just as long as it's not out of memory, which is usually set up a larger batch size. But for learning rate, you have to tune much more carefully. What happens is a larger rate, right, converges fast. That's based on, but you have oscillation. So small learning rate slow, but it doesn't oscillate, right? So what is so-called learning rate schedule is you go from fast to slow. Right. First, you can oscillate more, but it gradually quickly get you somewhere closer. But even it oscillates, it's still manageable. And then in the end, you try, but because it oscillates at a lower level, right? So if you look at the earlier picture, when you have a large learning rate, you can go very quickly. Even starting oscillate, it still oscillate at a lower level than very, very smaller. Then you just gradually decay. So, how do you set up a learning rate schedule is a research topic, and also it's a practical topic, both being investigated. There are solutions about that, and the different learning rate schedule, both based on theory and based on practical things, which we will not look at them very detailed, but we will look at a simple one, simple schedule. Okay. So let's try to look at. You take a larger step size in the beginning and taking a smaller step size in the end. So basically, this is the intuition. And there are so-called learning rate schedule, which actually try to implement this. Okay, try to implement. Yeah, basically this is I think I will go very relatively quickly. This is a learning rate schedule with SGD. Then we will show a simple schedule, and you can so instead of a constant learning rate, you just change it to T. And T is schedule. And how do you write? We will see in the end of this class, we will have one code which has there are specific in the PyTorch. There is a scheduler. And each time you are doing, remember we are doing the optimizer has to be updates, right, each time. And the scheduler also needs to be updated. What is updated? Updates is learning. So essentially, they will both need to be updated each time. This model parameter updates according to current scheduled learning rate. And the learning rate can be updated based on the scheduler. Okay, so that's the implementation. Usually, this scheduler goes to 0. Okay, so that's the usual. But you could also sometimes set up a constant learning. But essentially, it's a random partition. Again, yeah, this one we will not mention further. But basically, learning rate can be tuned. Usually, how frequent you tune, right? Because you can set up a learning rate scheduler. Scheduler can actually tune the any based on whatever that does. I mean, it could be each batch, it could be each epoch, it could be a few batches. But typically, you can tune the per batch or per epoch. Epoch usually is okay as long as your data is not too large, right? So if we do that, we can take a look at one particular schedule, right? So-called step decay. Step decay is based on the epochs, right? So it's but you could make it steps as well. But essentially, a few epochs. This is 100 epochs. A few epochs, you do a jump. Essentially, each time, this one basically says every t epochs, you reduce the learning rate by a gamma factor, right? Here it's a gamma equals 0.5, which means every 100 epoch, you reduce by a factor of 2. Factor basically your times factor of 0.5. Then you're starting with this guy. After 100 epoch, it becomes 0.1. After another half point, becomes 0.05, and so on. So basically, this is a learning rate schedule. How does it work? You can compare with a constant. Constant, this guy goes here, right? So this is a larger learning rate. This is a smaller learning rate. The reason this one goes faster is I think this one is special, is more stable because but basically when you have learning rate scheduler, you're first starting here. When you decay, sometimes you see a drop, immediate drop, because of the noise getting smaller, and the combined effect turns out to be something drop. Okay, and then you see that. So here is just the learning rate schedule itself, which you can observe. So yeah, so basically this is one typical scheduler. SCAD-PK has been used for some application, but there are other schedulers, right? More recent for transformer, LLMs, cosine scheduler, and also like linear scheduler become more popular. And those are different ways, and you can take a look. So they have a couple of different schedulers, which people use, but the idea is you decrease to zero. So that's basically the idea. You make a learning rate larger first and smaller. And this try to solve the problem of learning rate under issue. So now we are pretty much done with the learning rate and batch size. Those are the basics, right? Remember what at the beginning of the class we talked about? There are two important concepts. Learning rate and the batch size certainly are important. It just it's originally in the SGD, right? Here is in addition to SGD, what else you have? One is a momentum, the other is a graph, right? Adapt gradient. These are the things, and momentum is a more classical. It exists at least in the 80s. It already exists. It's an effective way to do that. So how do you do that? So basically, you have a learning rate scheduler, right? Momentum is a parameter. Usually, you do not tune the momentum parameters. It could have a scheduler if you want, but people don't do that. Usually, just pick beta. Beta is closer to 1. Typically, it's 0.9, 0.99, and so on. Something like that. Okay. Then you have a mini batch, right? We know that, and the initial is always given by your model, and there is so-called momentum, which is the P. We will starting always from 0. Okay, so that's what you're starting with this setup, the hyperparameters. Now you are updating. So if you look at the formula, what it does is first this is the momentum. Yeah, we write P. You can also write at M. I think even atom is M. Yeah. Later on we'll talk about them. So here P, right? So basically it shrinks your. Essentially, if you look at this, it's kind of a weighted average. It's a moving average of your past gradient. This is each mini batch gradient. When you shrink, beta is smaller than 1, so you shrink the previous one, adding this, essentially accumulate, but the accumulate is finite sum, right? Basically because of the shrinkage. So like you have a shrinkage beta, usually it's like 0.9, which means after 10 epochs, roughly there's a substantial decay of P. So basically, yeah, basically it's a weighted average. Essentially, you are trying to smoothing out your gradients here, right? So moving together. Another effect, because you have beta times this guy, you have this kind of moving average. What happens if let's say beta is 0.9, right? You will remember remember all previous 10 steps. 0.1, 1 minus 0.9. Over 0.9 over 1 is 10, right? So each time you forget 1/10 of your previous, then you can think about this one actually has a larger overall gradient. But because you are averaging, you are smoothing out your noise. So that is somewhat allowed in this case. Once you do that, right, you can accumulate gradient instead of using the current gradient to do your updates. In the momentum algorithm, this one again is still weight decay. It doesn't change. It's just because this derivative doesn't change, so it's still decaying your weights. And you just instead, but your loss, instead of using the current gradient, you're using the accumulated gradient, the past gradient accumulated, and this smooths out your gradient. So this turns out to be a very good technique, which we'll comment next to say what it actually helps you. But the rough thumb is it gets you faster convergence. It tolerates a larger batch size, tolerates a larger. Actually, it tolerates the same eta, but the effective learning rate becomes larger sometimes. So that's why you could make the convergence faster. So this is what it is, and there are some theory about that. So this one you can build theory to say why it's useful and how it's accelerate convergence and so on. But basically, from a theoretical perspective, you just interpret the theory to say, okay, what is the intuition, right? Well, why it helps, right? So something like this. And again, this one is can be justified theory. So what it helps is instead of relying only on the current gradient, momentum has incorporates a fast gradient, right? It's average, smooth out the noise. So this is one. And the other one is also, this is actually what happens in the proof, the more consistent direction. Yeah. In linear algebra, there is something called conjugate gradient, have the same flavor. It's actually very similar. It's a conjugate gradient. If you talk about this algorithm solving linear equations, they are doing calculation. They are trying to, instead of changing the updated direction gradient, when you have a quick changes, you somehow try to make sure your gradient changing accumulate in the same direction, so that you are moving consistently instead of just oscillating, right? So this one basically says that. Effectively, because you're accumulating the gradient, when you set a learning rate eta, right? The effectively you can think that loosely as eta divided by 1 over beta, because you accumulate the beta gradients, or you can accumulate past gradients. And this effective learning rate is helpful. Basically, in the theory, you can show that actually it doesn't cause too bad instability. Basically means blowing up. We mentioned blowing up about the learning rate too large, but this can help that. So, yeah. Basically under suitable conditions lead to fast convergence rates. And these are just some loose intuitions how you need, but it's effective and it's used. It's heavily used, and it also used later on in the atom. But momentum SGD is a very classical methods which has appeared to be useful. So let's look at just see how it works, right? So for the effective momentum. So let's look at the by size equals 16, and we have the same learning rate. Right, so here is the same learning rate. Here is the momentum. You're starting with 0 is basically SGD without a momentum. Basically, you shrink beta times the previous momentum. Previous momentum is because it's 0. There's no accumulation of history. 0.9, 0.99 is a more typical number, right? And this guy just say larger learning rate, and just see smaller learning rate. This is 10 times larger. Okay, so let's look at that. Very slow, right? This guy. Again, this is what we saw before. It's just the same problem. And if you look at here, this one is actually maybe let's look at I think first let's look at this guy, right? This one just 2 beta equals 0. The red one has some oscillations. Because this is 16, so it's not too bad, as bad as what we see at the baseline 4. But here is you still see the red has oscillations. We want to see. Thanks. But it has oscillation, right? So here. Now let's look at what happens. You are increasing the beta, right? Beta is 0.9, which is this one. It's not seen too well, but actually, it's yeah, it's behave similar. You can think about the behave similar to this guy, because this is where you are showing the learning rate equivalent, even the smaller learning rate, but beta somewhat accelerate your learning rate, which mentioned, and because of this 0.9, it's more like this guy, right? So essentially, yeah, this guy you can see is converted much faster. And if you have too large, you have more oscillations. Basically, you will still see. But usually, you can say, oh, right. So this one you are changing the learning rate or changing the beta, right? There are some. I'm saying there's a conceptual equivalence, but in reality, changing the beta with the effect of changing the learning rate is in many problems, is a better way than you just changing making learning rate larger. Okay, so that's why you need a combination. So this definitely is there's a related effect by changing the beta to be 0 to 0.9 as like you're changing learning rate, but it's not the same, not exactly the same, because there's a smoothing effect. So yeah, so basically this is a test loss. I think it's similar. Yeah, this one just because everything is here, so it's a little bit harder to see. But hopefully, at least you get the idea about the equivalent. You actually improve your learning rate in some sense. This is just something else. But anyway, so this is about it. Now let's talk about the second. Okay, so this is the first one, right? Momentum. The second important one is this algebra. So algebra I mentioned is solving this vanishing gradient problem. So let's refresh this vanishing gradient, which we mentioned previously, but using the background propagation algorithm, right? Compute the gradient using the chain rule. We mentioned last time because of multiplication, if they are smaller than one multiplication, and that's a typical case rather than larger than one, you actually quickly reduce the gradient. You can check in the practice, and each layer, right, derivative is smaller and smaller. So the top layer will be the output will be okay, but when you go to bottom layer, it's very difficult to move, so it's hard to optimize, right? So let's say this is just hypothetical, right? Here is just say, let's say you have 10 layers, up to the top layer and up to the bottom layer, and each time you have a derivative of 0.5, then essentially quickly when you have larger layers, you get some, right? This is output, this is input, and the gradient each time reduced by a factor of 2, then you gradually reduce. So basically, when you do the optimization, this one is okay to optimize. This one you will be challenging if you use SGD, right? So this is a cause a problem. So you want to say, oh, if this layer has a smaller gradient, we need to have an upper update rather than smaller updates. This one also have upper update. So how do you do that? Right. So and this is basically the idea about adaptive gradient. It doesn't work at the layer level. It's work as a basically weight level, but roughly because the weight level gradient they have a trend of decreasing. Essentially, it will compensate as such. So the idea is if you have a smaller gradient, you need to make a larger updates. This smaller gradient, I have to make a larger learning rate. Right? If a smaller gradient, larger learning rate, then they compensate each other. The smaller gradient, larger. This one is a larger gradient. You have a smaller learning rate, right? They compensate each other. So you want to make sure your learning rate is adjusted according to the gradient size, historical gradient size of your updates. So that's the key part, is to resolve that using adaptive gradient. But here, if you use a standard SGD, learning rate is the same for all the parameters. This one doesn't get updates. You have a slow convergence in your optimization. Okay, so what we do is this is an algorithm for the mini batch, the SGD, right? So this is our objective function, and we will look at this. You first set up the G. G is your gradient. This is the G is gradient, and basically what oh, actually something is sorry. So this one, yeah, I think I messed up this notation. This one is yeah, because I think I used the same notation, which is bad, but yeah. So I think this one should be a different symbol. Okay. This one should be a different symbol. Yeah. I will change that. Yeah. Maybe call it V or something. Basically, yeah. Basically, you compute the gradient, right? This is your gradient. This is accumulating of gradient square. So this one should be called V or something. So let's call it V. So I will make change. I think the symbol is not quite right. And essentially, V is accumulation. This one will be V. This one will be V. This is G. G is a square. Basically, each V accumulate the gradient square in the history. So the larger gradient, you have a larger. Then you divide that by. Once you divide by this, each learning rate balances. So this is the idea about adaptive gradient. The original paper is given in the reference. But the reality is that there are definitely issues with this original version, which people, I think the idea itself is fine, but then the way of specifically setting about this one, people change. We will soon cover. This is so how does AdaGrad alleviates the vanishing gradient problem? The neural net, earlier layers have smaller gradients, later layers have larger gradients, right? So if you calculate the amplitude of gradients, SPD will be, when you have the depth going, it will go down. AdaGrad, actually what it does is it will divide by the size of your gradient. Your gradient divided by size gradient is almost constant, historical size. So AdaGrad, if you look at what the amplitude of updates, it's almost always a constant for all the parameters. Rather than gradient, SGD will be different. Because it will using the historical gradient as your proxy of the size of your gradient, you divide by that. Once you divide by that, you actually get your actual gradient. So yeah, yeah, this one. I mean, in reality, this G should be the yeah, should be the yeah. I think I'll make changes. The other one is RMS prompt, which is a slight modification of that. This one is well known in the neural net literature. It's not a published work because it's just more considered as an engineering little bit of modification of AdaGrad, right? The main part of this AdaGrad, the formula we see before, is that this learning rate will decay. You just add a historical up. Once you add a historical up, it will decay too fast, basically. it will just adding, it grows linear with t. Grows linear with t is not what we want, basically. What we really want is this guy. Yeah, again, the symbol I need to fix, but essentially, what we really need is to do like a weighted average, right? This gamma plus 1 minus gamma will be a weighted average. Once you use a weighted average, this one doesn't grow, right? This one grow linearly, the right hand side grow linearly, while in the bottom it doesn't grow. It's basically stay constant with respect to the. And this is useful. So once you stay constant, you can apply a separate learning rate schedule without affecting. This one, if you look at the learning rate schedule, it's more like the learning rate is 1 over square root of t, because you divide by this accumulation. So and the accumulation grows in t. So it's a learning rate schedule is like 1 over square root of t. But if I do this, I can do a separate learning rate schedule. I can use anything. I can use step decay. I can use linear, whatever. I do not have to use 1 over square root of t learning rate schedule. So this is why. Another thing about this one will be useful is because you do a weighted average, right? Instead of just accumulating about the historical gradient, you can put more emphasis on the more recent gradient. So which when your landscape changes in your optimization, it can be helpful simply because the more recent gradients are more important. The more historical gradient using this formula will tend to be forgot. So this is how it basically to prevent the learning rate to become too small. Because in the original undergrad has an effective learning rate schedule of 1 over square root t, while RMS prompt, you keep this weight constant, you can do arbitrary learning schedule. Right. So the bottom line is one using the sum of square gradients, the other one you using the moving average of square. So that's the only difference. So this is more considered as engineering instead of anything else. Now let's move on to the key part of Adam. Then we will talk about the Adam algorithm, right? So RMS prompt adapts the learning rate with an exponentially weighted moving average of a square. So this is one idea, right? Certainly RMS prompt, again, it's not published because it's considered engineering modification of Adam. But this is a useful modification from practical side. And this is one idea, right? And this one solves the vanishing gradient problem, right? So this one is directly solving that. And another idea is this momentum. Momentum smooth out updates. You're achieving a larger effective learning rate and without blowing up. So momentum has some separate benefits. These two ideas are orthogonal. They are not the same. And on top of both, you can do learning rate schedule, right? And that's in addition. So we want to use these two ideas. So Adam say, okay, why don't we just combine both, right? So that's all. Yeah. So Adam, what's interesting is the original paper is there are some. I mean, people say, oh, that seems to be simple, just combining A and B. But it turns out this combination is so powerful that almost no algorithm can beat us, basically. But certainly the idea was already there from the Adam, but it's just the combination of those make it matter. Essentially, it does the following. Momentum term accumulate past gradients. So this is a momentum update. But then instead of using the momentum SGD, using adaptive learning, in particular, they use RMS prompt to adjust for different parameter scale, which will solve your vanishing gradient problem. The benefit of this Adam is you have a larger effective learning rate, which is basically one sentence interpretation about why you want to use momentum or gradient accumulation. And it's also insensitive to gradient scale, which is basically coming from the adaptive learning. So this one make it when you have a deeper networks, or also more difficult to optimize networks like transformers and so on. This is really the default methods, which needs to be applied. Okay, so that's basically the add-on, right? So then let's look at the algorithm. The algorithm. Add-on for just doing this. And again, it's the same optimization problem, which we are considering. They introduce other parameters, right? One parameter is a momentum, right? We call it the other one. We call it gamma. But for the RMS prompt, but it's actually the beta here. Essentially, it's just a moving average of your gradient magnitude. So here is we first computed the gradient. This is the same, right? So compute this gradient. Now let's doing this guy. This one is momentum. We call that momentum. Previously we call that P, but now it's calling the M. So maybe I will make it. I will change a little bit of slides, make it all consistent. Previous we also call that instead of P, call it M. But this one is this guy. They also use a moving average, but then this is the way it's using. And then there's this guy is called V, right? So yeah, originally we call both G, but now it should be called V. V is of a G gradient, right? This one is square, moving average of square. Yeah, so this one is this, and here is something. So okay, so maybe you can say why you do this, right? So maybe you're starting with this 0, and this particular formula. Eventually, 1t is large, right? This typically is 0.99 or something, right? So after 100 steps, this gradually this one will phase out, right? This one beta to the t comes almost 0 after a large number of steps. But the initial, why you do that? You can think about it. So basically, if you think about that, when it stabilizes, this one should have the roughly scale of G, right? But each time, because beta is close to 1, so each time if you're starting from the beginning, it gradually starting accumulating. It's starting with a very small, because this is 0. If you're starting with the first, and then this one is small, and gradually when you accumulate that, it's small, so therefore it's really gradually from 0 moving to some stable point, which is more of a scale of this. V is starting from 0, moving a scale points more like that. And to compensate, to make all the M, V about the same, you compensate by removing this bias, the initial bias. Okay. So then you divide by that. If both of these are constant, this one will keep a constant. So roughly, this is just to make sure your scale is about unchanged. And here is what it does, right? Here is basically what it does. So yeah. So basically, instead of in the undergrad, you minus G here, you minus M. M is accumulated G. It's moving average. Again, it can be compensated. So this is about what it looks like. This is basically the Eldon. The Eldon algorithm turns out to be one of the most effective algorithms in all the actually basically the deep learning, so the most widely used algorithm, especially for the more difficult to optimize, like transformer almost always has to be done. But we also have atom doublet, right? Mentioned. So what is the difference? So what can go wrong with this algorithm, right? right? So we can think about that. What can go wrong? Go wrong actually requires some theory. It's a subtle theory. So which is a little bit harder to explain now, but I can later on we will do again doing just like a momentum requires some theory. You can play around, you can show the convergence rates and so on. Here, this also a little bit. You need to understand why this one has some not most desired. The not desirable port from here to atom W is solving is not about other thing. It's more solving about the regularizer. Is this the right regularizer? Turns out the L2 regularizer, right? If you do the weight decay here, it's not theoretically it's not quite compatible with the atom. There are reasons for that. I don't want to explain why. But this one, you are doing this L2, you get this. You are shrinking at the G, not shrinking at the weight level, right? You are shrinking at the gradient level, but because you are doing adaptive. So this gradient, the shrinkage effect here is becomes a little bit different. It will be divided by this guy, right? This one is the same as it's a theta, right? It's a lambda times theta. So it will be your shrinking, and you move that here, then somehow it's a less funny. There's a little bit funny effect. And the atom W try to fix that. So we will look at and here, right? So atom. We see this regularizer, and which when moving here, there's something funny, and this funniness is actually has some theoretical basis for that. And you want to say, this is not the right way to do that. We do that. This one turns out the atom W is more of a procedure. The regularizer, effective regularizer is not L2 anymore, but just so instead of you are thinking about the procedure. The procedure as follows. Now, you still have weight decay, atom W, but the gradient computation doesn't incorporate your weight decay. It's not here, okay? It's actually in the bottom. These are the same. These are identical. These are different. You remove the weight decay. You just add it here. So this one is like a real weight decay. Weight is 1 minus eta lambda times and plus minus this guy. So this is basically because of the way optimization works. If you say, because I actually do a weight decay here, right? You do a real weight decay here, and this has have a regularization effect, making weight small. But the way it's writing is a little bit different. It's not the same as the L2. But you can argue that it's more compatible regularization. The effective regularization is more compatible with this algorithm. So atom W is a fix of atom just by changing the weight decay where you should. And to be honest, the once you weight decay, atom W are more preferred over atom, right? For practical reasons, and it just this one stabilizes better. You just shrink weight directly. So intuitively, it's just looking better, right? So you actually shrink that one. You don't know the other one, right? But so this is a really fits the description of a weight decay. Also, on the other hand, it's theoretically it's you can say it's nicer. This one looks better as well. So basically, yeah, basically this is what it looks like. And this one is actually default. So not the atom, but the slight modification of atom with how weight decay. This one is more natural weight decay. Make it more natural. Okay. So I quickly mentioned that I don't think we want to go too much about atom W, but just say naturally, if you look at the formula, it really implements original so-called weight decay. But what happens intuitively, if you explain the theoretical ways more intuitively, you say, okay, atom is there's a so-called coupled weight decay. When you move that down to the actual formulation, it will divide by your gradient accumulation. And that gradient has both weight and loss, right? It's not nice. So basically, we don't want those coupling. We want just the pure weight decay. And basically, yeah, basically because Atom is just naturally using the optimization. Weight decay is mixed with adaptive updates, which causing some coupling, right? It's not theoretically somehow it's not as desirable. Atom W, it's not desirable in the sense it doesn't, the L2 regularization doesn't really fit well, with this what Atom trying to resolve. Atom W decoupling directly parameter is just a more original idea of weight decay. If you interpret what weight decay is, just decay the weights, and then this is more direct, no longer in basically entangling of these two, and this is implicit regularization effect more consistent with adaptive gradients. So those are other good. The best, actually, so why people use MW? I mean, practitioners, I mean, they don't care about the one formula versus another one, as long as which one works better is better, right? So because they are all the same computation, there's nothing else discrimination, but often it's a better performance. And that's why that's being taken. So I want to say always, but usually this is the default. Default is not Atom with decay, but Atom W. Okay. So that's that's basically the conclusion of that. And so what is your method of choice, if you think about that, especially for this course? Probably I would say just Atom W with weight decay. If you set weight of decay equals 0, Atom W is the same as Atom. So that's the end of the conclusion. Let's move on a little bit about the code. Just quickly talk about. Any questions about this? Right. I think all that summarized is you use this algorithm. You have learning rate. You have a batch size. Right. You have a learning rate schedule, batch size. You have. We didn't talk too much about beta 1, beta 2, and those are also matters. And also we have weighted decay parameter percent. Those are the most useful. Here is an example, right? So we just use Atom W, right? So this is a data loader. Data loader, all it says is a follow. So you give your data set, right? What it does is try to partition the batch size. Remember, we do random shuffling each run and partition 2 batches. So that's all it does. And in the end, the last batch, you could either decide to ignore that or decide that to keep that. So that's basically general with data loader. The loss and the optimizer. The loss is cross entropy here, right? So, and the optimizer is Atom W. You always pass the trainable parameters. That's where they do updates, and that's where they get gradients from. Learning rate. So there's at this point, they just initial learning rate. Okay. Betas, these are typical. Beta 0.9, 0.99, or something, right? So one is for the momentum. The other one is for the gradient accumulation, the gradient square accumulation, and this is weight decay. So basically, yeah, this is a very typical setup, you know. And scheduler, this one just say how to use scheduler. This one just say it's a step scheduler, using basically every step, every 100 steps, you get 0.5, right? And then your gamma equals 0.5. Then they will look at this learning rate of your optimizer. They will try to modify each time once you call that, right? So basically, there's a learning epochs, and this guy is training, and you use your data loader, right? Each time you get one batch of inputs, one batch of targets, and this one we will talk about last time. This is the model forward loss, computing loss backward, get you the gradient stored here, dot grad. Okay, so and once you have that, you can do the optimize step, which does this exactly Atom W optimization, which is basically these updates. Okay, these updates is just getting you. And then you also do schedule updates for, yeah, I think that these are about Apple. this one, yeah, I think it's, I don't know. Okay, maybe there's something wrong. Step size. 100 epochs. Oh, this is 500. Yeah, I think that's okay. Yeah, it's 100 epochs reduced by one step. Okay, so then that's all. Yeah. So yeah, we are. I think we are done. So basically, again, you can look at some other book, but this one summary, and this one is the final one we talk, and you can see the progress through the few papers we mentioned. So that's all. Okay.